Now, there are two versions of stoichiometry, kind of beginning stoichiometry and definitely intermediate stoichiometry. Now, between now and Friday, I want you to put a lot of time into beginning stoichiometry, because intermediate stoichiometry is much harder. And if you don't understand the beginning, it will be significantly harder. So I want you to really put some time in doing practice problems. I'm going to give you some worksheets, additional worksheets as well. It's really important. Okay, are there any questions about anything? Okay, you'll like, for Saturday, folks, you'll like your lab. It goes along pretty fast. It's a pretty easy, straightforward lab. Good lab. All right, so let's jump into this. Okay, so stoichiometry. It's the mathematical relationship between products and reactants. And what I mean by mathematical, I mean a molar relationship. Again, moles come into play in chemistry, physics, molecular biology. It's moles, moles, moles. Okay, so I want to go over problem solving. We've been doing this whole semester. We usually skip number one. We go, what's given? What are we trying to calculate? Then we do the setup. Now, we're going to be doing number one. We have to balance the reaction. Now, up until now, we haven't had any chemical reactions going on. It's just been, water at 5 grams. How many liters, gaseous liters is that? And water hasn't changed. From now on, though, there's a reaction going on. And this is why we balance chemical equations, because there is a reaction going on. Now, in this class, I will give you the reaction. In 1A, possibly 2A, and 3A, you will not be given the reaction. It'll be a description of the reaction, and you'll have to read out the reaction based on the description, which is a jump. So when they say water, oh, that's H2O. When they say methane, oh, that's CH4. So there's some basic chemicals. Now, I used to, in this class, and I stopped doing it, I had a list of common chemicals see around the house. And I think next semester I'm going to reinstitute that. But anyway, and on there was methane and obviously water, things like what's a fat, what's an oil, what's bleach, just a bunch of common chemicals around your house. And you had to know both the name, the chemical name, and the formula. Okay, so bottom line is look for the equation to balance. Now, today we're going to use a very simple equation. And we're going to use the same one each time, so we don't have to keep balancing it. Okay, so a typical stoichiometry problem . Okay, 15 grams of water is formed. How many grams of methane is consumed? Okay, so this is the formula down here, or the reaction. Okay, so number one, balanced equation. Is the equation balanced as written? Do a real quick inventory. Here we have 1, 1, 4, 4, 4, 2 and 2 is 4, so it's balanced. Now, always assume it's not balanced. Always assume it's not balanced, including this class. Now, this one I just happened to balance real quickly for you. All right, so this is methane, CH4. So we created 15 grams of water. 15 grams of water. So what is given? Okay, step one is balance equation. We balance equation. Step two is what's given? 15 grams of water. Now make sure you put the water up there above the given in this case. Okay, what are we trying to calculate? Grams of methane. Grams of methane. So now we need to go from water to methane. This is where the balanced equation comes in. This is exactly why we have to balance equations, because there's a step in this process which looks at the ratio of the coefficients from the balanced equation. Okay, so just a quick side note here. So balanced equations. What information does a balanced equation give you? Gives you molar relationships and molecular relationships, not mass relationships, not liter relationships, only these two. So if you're not in moles, you got to get to moles. So we're starting with grams of water, so we need to get into moles of water. So step number one is going to be convert the given to moles. Grams have got to cancel. 18.02 grams in a mole of water. That's molar mass comes from the periodic table. We have okay, so you have two hydrogens at 101 apiece, one oxygen at 16 apiece. That's 1802 grams per 1 mole. Okay, now we're in moles of water. Now we can talk about the molar relationship between water and methane. And we get that from the balanced equation. So the ratio of the coefficients. Now methane is 1, water is 2. So that relationship is 1 to 2. That's going to go here. So the question is, what goes on top, what goes on bottom? Okay, well, since water's got to cancel, we're going to put water on the bottom. And the methane on the top. Okay, so this is, first step is to say the given to moles. Always, whether it's liters, molecules, whatever, take it to moles. Second step is the ratio from the balanced equation. The ratio of the coefficients from the balanced equation. Okay, now that the water cancels, we have moles of methane. We want grams of methane. So now we need to go from moles to grams. So methane is CH4. So we have 1C at 1201, 4 waters at 404. So that is 1605 grams per mole. Okay, so now we need moles needs to cancel. So now we have grams of methane. What are we trying to calculate? Grams of methane. So here we have 90% of the credit right here, the setup. So it's 6.68 grams of methane, 3 sig figs. Now, that's 3 sig figs, 4 sig figs. What about sig figs for 1 to 2? How many sig figs is that? Infinite, because it's exactly 1 and exactly 2. And then this would be 4 sig figs. So our answer is going to be 3 sig figs. Now that is as simple as it gets for stoichiometry. This is beginning stoichiometry. Again, I want to reinforce what I said earlier. You absolutely need to understand this before Friday. And what Friday is going to be, I'm going to give you 2 given, not 1. So it goes into from 1 calculation to 4 calculations. And they're all going to look similar to this. So you need to understand this to start with. Okay, any questions about this? I'm going to do a bunch more examples here. Okay. Now I'm going to continually use methane burning just because it's the same formula and we already know how to balance it to make life easier. Okay, if 15 liters of water vapor are formed, how many liters of methane were used? And everything's at STP. Now, when things burn, things are not at STP, but in this class, all gases are at STP. Now, our lab next week is on gases. It's a very easy lab. It's all observation, a real fluff lab. Okay, so what's given? What's given? Well, there's only one number there. Don't everyone speak at once. .6 liters of water vapor are formed. How many liters of methane were used? We're going from liters to liters, gaseous. What conversion factor are we going to be using for that? 22.4 liters, exactly. Okay, so first step is given to moles. Okay. So liters cancel, gives us, now we're at moles of water. Now from the balanced equation, we want water and methane again. And the coefficients are 1 to 2. Okay, now we're at moles of methane. Now we need to go to liters of methane. Now we're at liters of methane. Notice the pattern is exactly the same. 3 steps, exactly the same. Now, when you do the alternate dry lab, you're going to be doing a whole bunch of these, probably 20 of these. And you're going to notice when you're all done that there's a pattern, exactly the same thing. 3 steps, given to moles, mole ratio from the balanced equation, and then moles to whatever you're trying to calculate every single time for stoichiometry. So this is given to moles. Mole ratio from the balanced equation. And this is going to be moles what you're trying to calculate. 3 steps. Okay, I'm going to emphasize the pattern. Now, we're taking advantage of the fact that balanced equations are a molar relationship or a molecular relationship, not a mass relationship at all, not a liter relationship at all. It's a molar relationship. So if it's not in moles, get it to moles. Okay. You guys have any questions about what we're doing so far? Okay. How many molecules of carbon dioxide are created if 34.5 liters of water are created? Notice I said created twice. That means everything is on the right side of the equation. So this is the equation again, balance. We have methane, burning an oxygen, creating carbon dioxide, creating water. What's the given? The only number there. Starting to catch on. We're trying to calculate number of molecules of carbon dioxide. Number of molecules. That's Avogadro's number, 602 times 10 to the 23rd. Okay, so we're going from water to carbon dioxide. Okay, so water is 2, carbon dioxide is 1. The ratio is 1 mole to 2 moles. Okay, given to moles, first step. Now we're in moles of water. Now we need to go moles of water to moles of carbon dioxide. Okay, and from the balanced equation, it's 1 to 2. Now we've got moles of carbon dioxide. Now we're going to go to molecules of carbon dioxide. So again, given to moles, mole ratio from balanced equation. And then this is moles to calculate. 3 steps again, yeah. That's all gases at standard temperature pressure, STP. It occupies 22.4 liters in 1 mole. That you have to know. Commit that to memory, along with the 602 number. All right, it's a matter of grinding this thing out here. Okay, so 3 sig figs, infinite sig figs, 3 sig figs. So our answer is 3 sig figs. 3 parts again. Pattern city. Now you've got to do a whole bunch of these so that pattern is like cemented in. So as soon as you see this, oh, it's a stoichiometry problem. It's in 3 parts. Boom, boom, boom. Oh, it's a stoichiometry problem with two givens. We've got patterns again, but it's just more complicated. Okay, how many kilograms of carbon dioxide are produced from 23.4 liters of oxygen gas? Now, whenever we say oxygen in your 1A, 2A, 3A class, they're not going to say oxygen gas. They're going to just say oxygen. In my class, I always say oxygen gas, so you know it's O2. There are 7 elements that form diatomic gases. That's the list of them there. And you're going to have to know that for 1A, 3A, or 2A. 2A depends on your instructor, but for sure 1A and 3A. And oxygen gas is one of them. It's O2. So there's hydrogen gas, oxygen gas, nitrogen gas, and all the halogens. Okay, so this step, we are starting with liters of oxygen again. And we're trying to calculate kilograms of carbon dioxide. And we've already done liters to grams. So we just have an additional step of going grams, kilograms. How many grams are in a kilo? 1,000. 1,000 grams in a kilo. All right, so first step, like always, liters to moles. And again, since this is a gas, we're going to assume it's at standard temperature and pressure. So that'll get us to moles. Next step is the ratio from the balanced equation between oxygen and carbon dioxide. So that's a 2-to-1. Now we need to go from moles of carbon dioxide to grams of carbon dioxide. Carbon dioxide is going to be (44.01 grams from the periodic table. And okay, and once I get grams of carbon dioxide, I need to go to kilograms. And moles cancel. Everything cancels except kilograms carbon dioxide. So we have 3 sig figs, 3 sig figs, infinite sig figs, 4 sig figs, infinite sig figs because it's by definition. All metric stuff is by definition. Okay, so any questions on that? Okay, why don't you do this one on your own? Go through the 4 steps, balance the equation, what's given, what are you trying to calculate, then do the setup. Now, what I covered yesterday, what I covered today, what I'm going to cover Friday and probably into Saturday, in 1A, they cover it in one lecture because it's review, quote unquote. If you've never had this before, it's one hell of a review. And they don't give you any practice worksheets. They give you a few problems and your textbook. And that's it. And this is why Chem A students do well in 1A, 2A, and 3A, because you get this over a nice long period of time. Lots of practice. And by the way, they're trying to eliminate this class. The state says this class is a waste of time. That's what the state says. The state doesn't want people hanging around campus longer than they need to. You should go right into 1A. And my argument to that is, well, what if they flunk? They're going to be there an extra semester anyway, and their self-esteem is going to be in the toilet. You think that's okay? Oh no, research bears out that what we're doing is correct. This is their answer to that. I've talked to the dean. I've talked to a legislative advocate through my retirement association. They're at the state level, and they're giving me the same BS that these type classes are going to be eliminated. So we're hanging on by a thread. Now, interestingly, Sac City has got a class called 300, same as this class. I taught that class before, and it's exactly like this. In fact, I use the same notes, everything for both classes. And that class is going to stick around because Sac City did some research on past years showing that prerequisites are good for their students. Yeah. Yeah. And see, they don't hear the anecdotes from students or people that teach the class. They hear anecdotes from legislatures who have, oh, my son's been in college for years. He's got a PhD. He knows about this stuff. That's what they say. Yeah. Yeah. And they last year they tried to eliminate the tutoring center for algebra. And one of my students, in fact, the one that did the tie dyeing of lab coats, she organized that thing. And there were a whole bunch of students there and some faculty was represented. And they kept it. Student advocacy. So anyway, if anyone ever mentions eliminating preparation classes, I'm not saying punch them in the face, but definitely argue with them. There's definitely a well-documented case to be made for that. I mean, I'm not going to suffer. They'll stick me teaching 2A probably or 2B or something like that. But it bugs me. And notice there's only one class of Chem A. Used to have 7 classes. When I first started here 3.5 years ago, yeah, there were 7 classes of Chem A. Now we have 1. Last semester was 1. Semester before that was 1. Last semester we almost had 2. We couldn't find an instructor, so they canceled the class. The class was full, double section. And that's another problem is we have not enough chemistry professors. Yeah. Yeah. I mean, usually in your clue, whenever you have, you'll say staff, red flag. That means you don't have anyone to teach it. They're trying to find someone to teach it. But at the point that that class schedule was published, they didn't have anyone. And they're just hard to find. One, you have to have a graduate degree, and you have to want to teach. Because if you don't want to teach, it's like a desk job. I like to teach a lot. I could have retired 11 years ago. Of course, I couldn't have all my toys, but still, I retired a while ago. So anyway, that's my soapbox. It's real important to have prep classes. And I just want you guys, particularly if you're around people that can make a difference. Like if you're ever at a function at the beginning of the semester where the dean's there, in a mixer, oh, hi, everyone, stuff. Talk to them. They're very easy to talk to, especially here. Her name is Stephanie Ortez. And and there's 2 actually deans. Another one her name is Megan. What's her last name? Anyway, there are 2 deans. One is kind of more involved. That's Stephanie. And the other one used to be involved, but she ended up taking a job as the dean, overseeing the museum and the new construction of the new science building and some other things. But anyway, if you're ever in a situation where you can talk to the dean, just tell them about prep classes being important. And I can't emphasize that enough. So. Okay. All right. How are we doing in this problem? All right. What's given? Yeah. Grams of carbon dioxide. Is the equation balanced? No, it's not. Now it is. So 567 grams carbon dioxide is given. And we're trying to go to grams of water. Grams to moles for carbon dioxide. Okay. Remember, carbon dioxide is, that was what, 64, I think. What? Oh, yeah. Okay, so 4401. Okay. That gets us moles of carbon dioxide. Now we need the ratio from the balanced equation of carbon dioxide and water. And that's going to be a 1-to-2 relationship. Okay. Now we have moles. Why doesn't the carbon dioxide cancel? Gotta flip it, right? Should be on the bottom. Now it can cancel. All right, now we need to go from moles of water to grams of water. That's 1802 grams per mole for water. Moles cancel gives us grams of water. That's what we're trying to calculate. Okay, 3 sig figs, 4 sig figs, infinite, 4 sig figs, answer 3 sig figs. Okay, again, pattern, 3 parts. Again, yeah. Because we're not dealing with gases. Which number? The okay, 1 carbon, 2 oxygens from the periodic table, decimal number. Okay, so it's just a matter of every one of these. Now, this is what Friday's lecture is going to be about. How many grams of water produced if 567 grams of methane and 5.23 grams of oxygen are consumed? 2 givens. Oh, I erased all the calculation. Anyway, this is a 4-step process for calculation. So unless you understand today's, this will be very difficult to follow. Now, I'm basically done for today, but I want to show you where you can get some practice. Okay, so we're in Canvas files, stoichiometry worksheet. Stoichiometry worksheet. We haven't talked about empirical formulas yet. Equation balancing worksheets, gas stoichiometry problems, gasoline combustion problems. These are all stoichiometry, gram stoichiometry. Gram molecule story. I mean, there are, and all these have answers. I'm giving you lots of practice. Now, one other thing. This is the lab substitution worksheet. Okay. Mass stoichiometry problems. That's what we're doing today. So the lab called net ionic equations. You do this one instead. Now, these are all stoichiometry problems. I want you to look at the answers. 3 parts. Every single one of these. 3 parts. Pattern, pattern, pattern. Grams to moles. Mole ratio from the balanced equation. Grams, moles to grams. I mean, they're all in 3 parts. All of them in 3 parts. So this last one here is converting the grams to kilograms, but on the front end. But basically, 3 parts. Okay, so this would be a good worksheet. You need to do this anyway for the dry lab, so you might as well do this between now and Friday. Because let me show you what Friday is going to look like. Okay, sounds simple enough, right? Methane is fully combusted to water and carbon dioxide. That's what we've been doing all day today. That's the equation. Balance it. 15 grams of methane and 15 grams of oxygen react. 2 givens. What's the limiting reactant? How much excess reagent is left over? So this is what it's going to look like. This is all for one problem. We have 2 calculations to determine what limits the reaction. We have another calculation here to determine the excess, what's left over. Then we have another reaction down here looking at the excess. And the only thing missing is theoretical yield. I'm going to go over that on Friday as well. But this is why you need to understand today's lecture. It's because we're going to be doing 3 of them plus an excess plus a theoretical yield for every limiting reagent problem. And you're going to have 1 on the test. You're also going to have a take-home problem. But test 4, this is all it is. Very focused, unlike test 3, which is kind of like all over the place. This is extremely focused. And the reason why it's extremely focused is because this is a real weakness for 1A, 2A, and 3A students. And this is what they want me to focus on, and I totally agree. Yeah. No, we're covering limited reagents on Friday. And then the test will be a week from Saturday, or 2 weeks from today. All right. So I just wanted to give you a flavor for what's coming up on Friday.